Suppose we've got a ball that is moving down with some speed v. And then later, after the ball collides with the floor, the ball's velocity is directed upwards. So the initial velocity is downwards and the final velocity is upwards. I know that if there was a change in the velocity of the ball, then the ball must have accelerated. And if the ball accelerated, then a force acted on that ball. And that force must have happened when the ball was in contact with the floor. The floor exerts a force F on that ball while it's in contact with the floor. If I were to make a graph of the force that acts on the ball, F, as a function of time, t, the graph might look something like this. It's 0 for a while, and then the force increases as the ball makes contact with the floor, and then it decreases, and then settles down at 0 once the ball has left the floor and isn't in contact with the floor anymore. This point here, where the force starts to be exerted on the ball, is the point where the contact between the ball and the floor begins. And maybe that happens at a time t initial. And then this point here would be the point where the contact between the ball and the floor ends. And I'll call that TF. And so what we find is that when two objects interact, when they collide like this, the force that's exerted on them from the ground or wall or between the two objects themselves, that force is not just exerted instantaneously. That force is exerted over a certain time interval. So here, that time interval, delta t, is TF minus TI. This point that occurs at the top of the graph here, at some maximum force, is the point of maximum compression. The point of maximum compression. You'll find this to be true if you ever take a slow motion video of an object colliding with another object. If you look at the point of contact between the surface and the object, you'll see that when the object makes contact with the surface, it really can be deformed. When somebody kicks a soccer ball or hits a golf ball or a ball is just dropped on a table, you can see that the object will become deformed. An object that might have been perfectly round as it was falling downwards might, when it makes contact with the surface, really become deformed in some way because of the large forces that are being exerted on the object while it's in contact with the surface. And then, of course, when it rebounds back up, the object looks the same way as it did when it was coming back down. So during the collision, there are forces that are acting on the object, and the force that acts on the object changes. Initially, it's a small value, and then as the object is more in contact with the surface, the force increases to a point where there's the maximum force at the point where the maximum amount of compression of the object is happening. And then that force decreases as the object leaves the surface and is no longer in contact. In my picture on the left, I'm going to add that force F acts over a time interval delta t. The product, F times delta t, is a new quantity that we're going to define, which is called impulse. For impulse, we're going to use the letter J, a capital letter J. And so impulse is equal to force times some time interval delta t. If you were trying to figure out what the impulse was that was delivered to an object, you would need to know the time interval and the force. But if you look at the graph, it might be pretty difficult to determine what that force is, because the force that was exerted on the ball isn't described by this F max value that I've displayed in the graph. That's just the force that's exerted at one point, which happens to be the maximum value. Instead, what we'll do is we'll define some average force value that acts on the ball. And so the force is somewhere between the maximum force and 0, and we could figure out an average force that was delivered to the ball, either graphically or if it was given to us. And so for that reason, there's just a couple modifications that we need to make to our equation on the left. First, instead of f, we should be using f average, which is either represented by writing the subscript AVG or sometimes with a bar over the top of the force symbol. And also, force is always a vector, and so I'm going to put an arrow over the force symbol. And because force is a vector, impulse also is a vector. And so this is our equation for impulse, which depends on the average force and the time interval over which that average force acts on an object. And so if we go back to our graph now with our updated impulse equation, we could say that if we take that same graph that I plotted up above, force versus time, and we have the same line where the force increases to a maximum point and then comes back down to 0. If we instead plotted the average force, which is a constant thing that occurs over some time interval, that average force would look something like this. The average force is, or the force that's exerted on the ball for a while is 0, and then at the point of contact, when that happens, the average force would rise up to its average value, and then when the point of contact ends, the force would go away. And so our graph would look something like this, where that red line represents the average force. And what we would find that this red rectangle has a height that is equal to the average force and a width that is equal to the time interval delta t. And so I hope that at this point, because this is the second or third time that we've seen something like this, that you're able to see that the area of that red rectangle is equal to the impulse that acts on that object from the floor. And so the impulse that is delivered to an object can be found from the area under the curve of a force versus time graph. When we actually do experiments like this, it might be difficult to find the area under the curve of the top graph, but if we knew what that average force was over the time interval, then we would be able to determine that a little bit more easily. Otherwise, we might have to break that top graph into different chunks that we can find the area of more easily. Looking at the equation for impulse, we should see that if impulse is F times delta t, then we could represent the units for impulse with newtons times seconds, because forces are measured in newtons and time is measured in seconds. But for reasons that we will see shortly, the units for impulse, what we will use is actually kilograms times meters per second. So kilograms meters per second is the unit that we will use for impulse. I also know from Newton's second law that the average force, F average, divided by the mass of an object is equal to its average acceleration. And acceleration is a change in velocity over change in time, which can be rewritten as final velocity minus initial velocity divided by delta t. If we look at a couple of the terms of this equation, the first one and the last one, and set those equal to one another, then we could rearrange this to look like the following. F average times delta t is equal to the object's mass times its change in velocity, v final minus v initial. And next, I'd like you to recognize that this term on the left-hand side, F average times delta t, is what we just talked about, the impulse, J. And so impulse is equal to F average times delta t, but it's also equal to mass times a change in velocity. So it can be written as m times v final minus m times v initial, where those velocities are vectors. And so we can think of impulse as being a force acting over a time interval, or we can think of impulse as a change in velocity that also depends on mass. This last term, m times v, is another new quantity that we're going to define. And this quantity, the product of m and v, is what we'll call momentum. The momentum of an object is defined as, we'll use the lowercase letter p for momentum. P is used for momentum, and momentum, which is a vector, is equal to the mass of an object times the velocity vector of that object. And so maybe here we can see a little bit more clearly with momentum that mass is measured in kilograms and velocity is measured in meters per second. And for that reason, we use the units of kilograms, meters per second for momentum. And since a change in momentum, mv final minus mv initial, is equal to impulse, momentum and impulse have the same units, kilograms, meters per second. And so lastly, I'd like to point out here that when we look at the equation that I've written above, J equals F times delta T equals M times the change in velocity, each of these terms, M times VF, that is the final momentum of the object, and M times VI, that is the initial momentum of the object. And so the impulse, which is all the way on the left, is equal to PF minus PI, which is a change in momentum of the object. The fact that impulse is equal to a change in momentum, J equals delta P, is something we'll call the impulse momentum theorem. So kind of like the work-energy theorem, we have an impulse momentum theorem. So any change in an object's momentum is due to an impulse, some force that has acted on it over a certain time interval.